Okay, so here we have another experiment. It's to do with metal girders, which are metal beams that are used in construction. And we're going to look at how the horizontal oscillations, the way that it vibrates backwards and forwards, varies with the height. And this relates to earthquake design. Okay, so let's have a look at the data presented as usual as a graph. It's super easy, drawing a line of best fit through the dots. Now, of course, this is not a line. It looks quite clearly like a curve. And if it looks like a curve, then draw a curve. And I'm going to try and do so. So hang on a minute. As I keep saying, it's very difficult to do this with this program, but if you can do this very carefully, you need to make sure that you go through all the dots. So this is unacceptable. Okay, you need to make sure that you do this correctly. Do it in one smooth line, none of this kind of rough, feathery strokes. It must be a really clean, confident line. So do it in pencil and use an eraser to make sure it's perfect, because it's a gift of a mark. The next part is a very common question, which is worth a lot of marks. So let's see if I can explain this clearly. It is hypothesized that the frequency is inversely proportional to height. So this is fairly common. They give you a hypothesized relationship, and you need to look at the data and see if that's true. Now, if frequency is proportional inversely to height, then if we write this as a linear equation, we get frequency equals k, constant, times 1 over h. And to simplify that, make it easier to understand, frequency equals k over h. Okay, now what does this mean? Well, if we make k the subject of the equation, we end up with frequency equals, frequency times height equals k. If frequency is inversely proportional to height, all these points on the graph should follow this relationship. Now it says quite clearly, choose two well-separated points. So I'm going to choose the first one, okay, which is 5, a height of 5 and 60. And I'm going to choose the last one. You can't get any further separated than that. Okay, so follow the instructions carefully. If I do the maths, we can see that for that first point, that we have 5 meters and 60 hertz. 5 meters and 60 hertz. And if we look at the second point that I've chosen here, we have 20 meters, and if you count carefully, down there, we have 3 hertz. And I'll rub this out so you can see that point clearly, but it's definitely 3. Now let's see how these match up to the relationship F H equals K. If I do that with the first coordinates, I have 5 times 60 equals 300. And if I do it with the next set of numbers, 20 times 3 equals 60. They are not the same. So therefore, frequency and inverse height are not proportional. Okay, so this is fairly common. You're asked to prove using numbers. So whenever you're given a question like this, go through the steps. Choose the coordinates, put them into the hypothesized relationship, and they should or they shouldn't either confirm it or disprove it. So here we have a new equation, which is possibly proportional. Let's have a look. Frequency equals k over h squared. And the first thing it asks you to do is to draw a line of best fit. Well, luckily I have finally been able to get my straight lines to work. So you can see here that it can actually be done. You can get a straight line through all the points, through all the error bars, and it goes through the origin. So this must be a proportional relationship. The next thing you have to find is the constant k. So I'm going to set the read-offs up for you. And what I've chosen is this first line, okay, this last point over this whole area here. Okay, so remember, show your read-offs clearly and make sure you show that they are bigger than half the line. Okay, so if I look at my points, I have 60 minus 0 over 40 minus 0 here. Okay, so I'm going to work that out, and I get 1.5 units. So I'm going to write the units on this side because I've got more room. We have on the y-axis hertz, and on the x-axis meters to the minus 2, but to the minus 1 because you're dividing frequency over height to the minus 2. So that gives me hertz meters squared. Crazy units, but you must show this in your working out. So the constant k is 1.5 hertz meters squared. Now the last thing you must do when you work out the gradient is to check that you haven't forgotten any other sections. And if we see frequency here has no other information, but here, shock horror, we've got 10 to the minus 3. So your value here of 40 was actually 40 times 10 to the minus 3. So the real answer is not 1.5, it's 1.5 times 10 to the 3. Okay, so I'm going to write it here, 1.5 times 10 to the 3. Okay, hertz meters squared. Okay, so always be really, really careful checking the axes and checking the scale of the axes. And of course 3 marks, you would have definitely lost one of those marks if you hadn't remembered the units. Last question, state one reason why the results of the experiment could not be used to predict the natural frequency for a height of 50 meters. Well, if you check your graph, it only goes up to 45 meters. And what's this question actually about? Well, whenever you plot a relationship, you cannot conclusively say that that relationship is in fact the case outside the parameters of testing. Parameters of testing. You can hypothesize that beyond 45 it will continue following that pattern, but unless you test it yourself and actually do an experiment, you will never know. Okay, so it is to do with the very nature of experimentation. Yes, you can make a conclusion. You can say that frequency is proportional to whatever, but only within the range that you've experimentally investigated. So what has this question shown us? It's shown us to be careful doing our lines of best fit, as usual, to be super careful reading our axes to make sure that we take all the information, that there isn't a 10 to the minus 3 that slipped beyond our notice, and once again, be very, very careful with the units of your gradients and your intercepts.